Hello, how's everyone doing? I'm talking to no one in the chat. Okay, so last week or like few days ago, I finished studying about sequences and series, and this time I would start learning about the power series. Last stream was mainly revision, but by the end of the stream, when I started talking about the ratio test and root test, I was slightly confused by it. Well, I was slightly confused by the proof of it. I don't think that chapter was really interesting for me. Hopefully, this one is better. I was just researching on how to resize the picture for the banner. Anyways, so we are going to start learning about the power series. So this is what we did last time, sequences and series. This time I will do power series. Hopefully it's more fun, I should say. An infinite series of the form some coefficient times x to the power of n is known as a power series. Since the terms contain the variable x, power series can be used to define functions. Okay. This problem always happens. Power series, a series of the form Cn x to the power of n. So coefficient. Okay, wait. Power series. Nope. Is it to infinity? That's an ugly looking infinity. So C some coefficient and then x to the power of n. So C is 0, C1, C2, and so on. Where x is a variable and the coefficients Cn are constants, is known as a power series. Series of the form Cn x to the power of n is a power series centered at 0. A series of the form Cn x minus a to the power of n is a power series centered at a. So this should be the actual definition, right? Let me just get rid of this. Also the size should be okay. N C0. Is a constant in all of them? Is there a different name if there's like a different constant in each term, like inside the brackets? Plus it with hold on. Plus it with C1 x minus a plus that with C2 x minus a squared To make this definition precise, we stipulate that x0 is equal to 1 and x minus a to the power of 0 is equal to 1, even when x is 0 and x is equal to a, respectively. Okay, so Cn over here is n factorial. So 1 over n factorial, and Cn over here is n factorial, and it's centered around 0. Power series centered around a. Convergence of a power series. Since the terms in a power series involve a variable x, the series may converge for certain values of x and diverge for other values of x. For a power series centered at x is equal to a, the value of the series at x is equal to a is given by C0. What? Oh, I see. X is equal to a, then all of this would be 0 and you will be left with C0. Therefore, a power series always converges at its center. Some power series converge only at that value of x. Most power series, however, converge for more than one value of x. In that case, the power series either converges for all real numbers x or converges for x in a finite interval. Okay, let me think. What do they mean by centered at? So Cn x minus a to the power of n. The geometric series x to the power of n converges for all x in the interval minus 1 to 1, but diverges for all x outside that interval. We now summarize these three possibilities for a general power series. Consider the power series Cn x minus a to the power of n. The series satisfies exactly one of the following properties. The series converges at x is equal to a and diverges for all x which is not a. The series converges for all real number x. There exists a real number r greater than 0 such that the series converges if x minus a is less than r and diverges if x minus a is more than r. At the values x where x minus a is equal to more than r, the series may converge or diverge. I mean equal to r. The series may converge or diverge. Proof. What is this proof for? I think it's trivial. These two cases are trivial. It could be one of these two. We know it could be one of these three, but what's not trivial is that if it's only one of these three. The set of values x for which the power series converges is known as the interval of convergence. Since the series diverges for all x where x minus a is more than r, the length of the interval is 2r. And therefore the radius of the interval is r. The value r is called the radius of convergence. For example, since the series xn x to the power of n converges for all values x in the interval -1 and 1, -1 to 1, and diverges for all x such that the absolute value of x is more than or equal to 1, the interval of convergence is -1 to 1. What are they proving here? We must first prove the following fact. If there exists a real number d which is not 0 such that CDN converges, then the series Cn x to the power of n converges absolutely for all x such that absolute value of x is less than absolute value of d. Since Cn d to the power of n converges, the nth term Cn dn goes to 0 as n goes to infinity. Isn't 2 and 3 the same? No, they are not. Because I think for number 2 is the case where the radius is infinity. But I guess number 3 they're talking about a real number radius. Therefore, there exists an integer capital N such that Cn d to the power of n is less than or equal to 1 for all n greater than or equal to capital N. Writing Cn x n, we conclude for all n greater than or equal to capital N, Cn x to the power of n is less than or equal to x over d to the power of n. This series is a geometric series which converges if this is less than 1. Okay, so they concluded if there exists a real number d, but what have they proved exactly? They only proved this statement, that it converges if x is less than d. Okay, with this result we can now prove the theorem. Consider the series a n x to the power of n. Let S be the set of real numbers for which the series converges. Suppose that the set S is equal to Well, there's only one element 0. Then the series fall under case 1. Suppose that the set is the set of all real numbers, then the series falls under case 2. I think my doubt about number 3 is uh, you may have some values of x minus a. Out of all the values x minus a can take, suppose a is here, and then what they're saying is that there's a radius such that this is r, and then this of equal length is r. Then as long as x is within this from to here, as long as x is within inside this, then the series converges. But my question is, how do you know it's not like one real number on one side and then another real number, let's say L, on another side, and then the series converges in this entire thing? Guess that's what they're trying to prove. They're trying to prove that this can't be the case. It has to be R on both sides. Series for, suppose that S is not just 0, then S is not the set of real numbers. Then there exists then there exists a real number which is not 0 such that the series does not converge. Thus the series cannot converge for any x such that the value of x is greater than x star. Therefore the set S must be a bounded set, which means it must have a smallest upper bound. Call the smallest upper bound R. Since S is not a set of one element which is 0, the number R greater than 0. Therefore, the series converges for all x such that modulus S x is less than R. The series falls under case 3. Yeah, I don't understand. I'll say accept this for now, and maybe when I learn more, I can look at the proofs. So converges here, converges for all values, converges, and then diverges. So then my question would be, how do you know it doesn't converge at a plus L? For each of the following series, find the interval and radius of convergence. Where x to the power of n over n factorial. This would be 0 factorial is 1. So 1. It's centered around 0. Hmm. Let me think about this. They're applying the ratio test. So this is equal to x to the power of n. So we are left with x n plus 1. So if we take this to infinity, then it's 0, right? Zero. No, wait. This goes, then this would be infinity, right? And then no, what am I doing? This goes to infinity. So it converges for all values of x. No, this is 0. For the second one, they applied the ratio test and got infinity. So the series diverges for all x not equal to 0. For this one, they got this. So as long as this is between 0 and 1, right? The ratio p less than 0 if x minus 2 modulus is less than 3. So x is between -1 and 5. Wait, hold on. R is 3, right? R is the radius of convergence. Could it be equal? Maybe. So the radius is 3. The interval is 6. The interval is from -1 to 5. Now at -1 and at 5, you have to find it separately. This is an alternating harmonic series. It converges. Thus, the series converges at x is equal to -1 or x is equal to 5. It's a harmonic series, which means it is divergent. So the interval of convergence is -1 to 5, and the radius is 3. Recall that the geometric series A plus AR squared and so on converges if and only if modulus R is less than 1. In that case, it converges to A over 1 minus R. Okay. You can graphically show how this series provides a representation for the function 1 over 1 minus x by comparing the graph of f with several of the partial sums of this infinite series. So what are they trying to show? This is a graph of 1 over 1 minus x. Sn is the sum from 0 to n of x to the power of n. S2, S3, S4. Oh, I see. Wait, hold on. Use a power series to represent each of the following functions f. Find the interval of convergence. S n x is equal to sum hold on, I don't need this. I need this. So let's see if I do 10. Oops. Let's just do 100. Or even a little increase. It shows. Is this the same graph? 15. Even when it's past 1, it still converges. Am I doing this right? Why is it so close even after 1? Does it converge after 1 as well? Okay, let's try to do this question. F of x is equal to 1 over 1 plus x cubed. So sum x3 and n is equal to 0 to infinity. I have this, I have this, I have no, 3 times 2 is 6, yeah, and then 9. 0, 1, 2, 3, 4. According to the geometric series, since the ratio is x cubed, you have 1 over 1 minus x cubed. Voila. What if I do this minus? So all of these becomes minus. Minus. So x to the power of 0 is 1. So I have minus 1 and the multiplying term is x cubed. So this is x cubed minus 1. But it's not x cubed plus 1. Yeah, I'm trying to represent this. Wouldn't this be first term, and then the next term is times minus x cubed, then the next term is times minus x cubed. So this is what we are representing by 1 over 1 plus x cubed. So it's convergent if r is less than 1. Minus x cubed is less than 1. So shouldn't it be x is less than 1? If you take the cube root of both sides, you will be left with x and 1. The minus isn't going to matter. The minus will just go away. Okay. Let me think about the next one. X squared for minus x squared. This is equal to minus 1 So for this, forget the minus. For this would be first term. And then the next term is 4 over x squared. And then the next term is 16. And I should do 4 squared. This 4 cubed over 6. I'm multiplying it by 4 over x squared. Now if I bring the if I'm multiplying negative 1 with this, then all of them would be negative. So this would be convergent if convergent if what? R is less than 1. If x is greater than 2. If the positive part is convergent when modulus x is greater than 2, then the same could be said about the negative part, right? Because if the entire series is positive or if the entire series is negative, then the interval of convergence intuitively it should be the same. But I could be wrong. Yeah. Wait. Wait, I think I did it wrong. This works if it's positive. If I do sum of four to the power of n I think if n were to go to infinity, this would be an asymptote. But this here is a radius of divergence. It didn't say, I thought only 3 cases were possible. Well, I guess This is different. This is not a power series. Representing a function with a power series. This over here is not a power series. This can be represented as a power series. Just this over here. Where Cn is either -1 or +1. But they never said anything about x being raised to certain power. It's x minus a to some power, not x cubed. So is this a valid power series? Because it's x cubed, not x minus a. It's x cubed minus a. What about this? Is this a valid power series? Okay, let's try doing what they did. X square over 4 minus x square. I don't need a line, it's the same thing. So this converges if R is less than 1. Four is less than 1. Square is less than 1. It's less than 1. Sorry, hold on. 4, 2. So this is the first term. This is the second term. So multiplied by x squared over 4. Okay, so I have several questions. One is that if you can call this and the other one a power series and this a power series, because what they said has to be some coefficient and then x minus a to the power of n. It never said like inside the bracket x has to be to some power. Like I can understand these. I don't understand the other one. Properties of power series. In the preceding section on power series and functions, we showed how to represent certain functions using power series. In this section, we discuss how power series can be combined, differentiated, or integrated to create new power series. Combining power series. Suppose that the two power series c n x to the power of n and d n x to the power of n converge to the function f and g respectively on a common interval I. The power series c n x to the power of n plus minus d n x to the power of n converges to f plus g on I. Um, for any integer m greater than or equal to 0 and any real number b, the power series bx to the power of n and cn x to the power of n converges to bm to the power bx to the power of n f of x on I. So I'm multiplying bx to the power of m, that converges to this. For any integer m greater than 0 and any real number b, the series cn bx to the power of m, all of that to the power of n, converges to f of b times x to the power of m for all x such that this is also in I. For case 1, converge. These two series converge to f and g respectively on the interval I. I think that's trivial. We have some series let's say some series, it's a divergent one, between 5 and minus 5. It's like this. So some series from 0 all the way to infinity, if you add them, you will get these values, and then there's a function f of x, just like the same on this interval. So it's like this. It's basically the same. So on these interval, this series converges between -5 and 5, but in this interval it converges to f. The orange line is f of x. And then you have another series, let's say like this, and it converges to f to g on the same interval. Then the sum of their series on that interval, like if we only consider this interval, sum of their function will lie, suppose it lies here, sum of the function lies here, but so would the sum of the series, that would also lie here. That's what the first case is telling us. Combining power series, suppose that an x to the power of n is a power series whose interval of convergence is -1 to 1. And suppose that Bn x to the power of n is a power series whose interval is of convergence is -2 to 2. Find the interval of convergence for the series these two combined together. I guess it would be -1 to 1, right? Since those are the common interval. And this diverges when x is equal to 3, right? So an 3 to the power of n would diverge, but if we also multiply x to the power of n, let me think about this. Okay, this one is a little confusing. This one I can understand, it's -1 to 1. Oh, I see. 3x should be in the interval -1 to 1. Therefore, the series converges for all x in the interval -1/3 to 1/3. Constructing power series from non-power series. Use the power series representation for f of x is equal to 1 minus x combined with combining power series to construct a power series for each of the following functions. Find the interval of convergence of the power series. Let's see. F of x is equal to 3x over 1 minus x squared. I need to convert it to non-power series. So when it's 1 over 1 minus x squared, this is equal to this, right? And that means I think I can get this. Then that means I have no clue what that means. If I do 3x plus it with 3x x cubed plus it with 3x cubed, we get this, right? And then if this is only convergent if x is less than 1. So then what? Then infinity 0, n is equal to 0. This, wait, x square and then multiplied with x square again. One, two, three, like that. And then x is, this is 2n plus 1. So this is the power series, x to the power of 2n plus 1. Oh wait, it's plus though. So minus, it's plus. Multiplied with minus x square. Multiplied with minus x square. Like that. Yeah, minus 1. Right, and since this is the case, don't think the minus would matter. And if we square root both sides, we get less than 1. So, yeah, the convergence is minus 1 to 1. To find the power series representation, use partial fractions to write 1 over x minus 1 x times x minus 3 as the sum of two fractions. You have this. Hold on. Okay. Finding the function represented by a given power series. Consider the power series 2 to the power of n times x to the power of n. Find the function f represented by this series. Determine the interval of convergence. This converges if this is less than 1. And this is 2 to the power of n, right? 2 to the power of n. Wait, that wouldn't converge. I don't think this converges. Maybe it does. So x is less than half. X has to be less than half. Yeah. Suppose you win the lottery and are given the following three options. Receive $20 million today, receive $1.5 million per year over the next 20 years, receive $1 million per year indefinitely, being passed on to your heirs. Which is the best deal that assuming that the annual interest rate is 5%. We answer this by working through the following sequence of questions. How much is $1.5 million received annually over the course of 20 years worth in terms of today's dollars, assuming an annual interest of 5%? So 1.5 so 1.5 plus it with, in the next year it will be 1.5 times it by 20%, so times 1.2. I'm multiplying it by 120, which is what I will get. Over the next 20 years. Sorry, it's 5%. It's like this. So first year, second year, third year, all the way till 20. So shouldn't n be equal to 1? Or should I make this n plus 1? Then shouldn't this be 21? Let's make this easier. First year I get 1.5. Next year I get 1.5 times 1.5. So how much is that? to the power of n 9,972 million. When they say interest rate, what do they mean by that? 5%. Wait, hold on. I'm wrong here. Shouldn't it be 1.5? It should be 1.05. I don't understand. Shouldn't you be multiplying? Therefore, the present value of that money P1 satisfies. Suppose you win the lottery and are given for the following three options. Receive $20 million today. Receive $1.5 million per year over the next 20 years. Receive $1 million per year indefinitely, being passed on to your heirs. Which is the best tier, assuming that the annual interest rate is 5%? Therefore, the present value of that money P2 satisfies. I don't get what they're doing here. Consider the payment of $1.5 million made at the end of the first year. If you were able to receive that payment today instead of 1 year from now, you could invest that money and earn 5% interest. Therefore, the present value of that money P1 satisfies P1 times 1 plus 0.05, which is equal to $1.5 million. Should it be 1.5 million times 1 plus 0.05 is equal to P1? If you had 1.429 and added a 5% interest, then you would get 1.5. Yeah, I don't understand. Multiplication of power series. Cnx to the power of n, dnx to the power of n. This. Okay, so you're multiplying them. C0, D0, C1, D0 plus C0, D1. Wait, what are they doing? C0, D0, C0, D1. In both of them, there is only 2x squared, right? Oh no, wait. C0, D0. And then C1x times D0 will give C1, D0x. Then D1x times C0 will give C0, D1x. In order to get x squared, you need x to multiply with x squared. Sorry, in order to get x squared, you need x to multiply with x, or x squared to multiply with no coefficient. Suppose the power series converge to f and g respectively on a common interval I. Let En is equal to C0. This is a different E. I thought this was the Euler summary. C0 dn, C1 dn1 minus 1, and so on. I'm multiplying the first coefficient here with the last coefficient here. Is equal to ck d n minus k. Then I already get this. Oh, I see. When we are doing this first times first. Wait, let me properly understand this. if there was only one, right? Suppose n is equal to 0, so the series just ends over here. Then the multiplication of the series is C0 T0. If we do n is 1, then there is C1x and T1x. For 0x is this. For 1x, we have to multiply first one with the last one, then first one with the last one. C1 D0 plus it with C0 D1x. For the next one, I want x squared over here. So what I will do is multiply first with the last, and then multiply first with the last. So x squared with no x, x squared with no x, and then 1x will make up x squared. And then if I want to do the third one, do x squared with this, c0 with t3, and then this here with this here with this, first and last, and then one back from here. Yeah, I understand what they're doing now. So E5 would be this plus this plus this all the way till 5. That would make sense. E3 would be these two plus these two plus these two plus these two. So 1, 2, 0, 1, 2, 3. This is known as the Cauchy product of the series. A lot of the proofs are too difficult to understand, or they are very difficult to prove. Multiplying power series. Multiply the power series representation with the power series representation 1 over 1 minus x squared. Let me see what they're doing. You need to multiply these two, writing on the first several terms. We see the product is given by 1. and got stuck. So one, writing out the first several terms. Yeah, I guess I can sort of see it. Okay, differentiating and integrating power series. Consider a power series that converges on some interval I and let f be the function defined by this series. Here we address two questions about f. Is f differentiable, and if so, how do we determine the derivative? How do we evaluate the indefinite integral? We know that for a polynomial with a finite number of terms, you can evaluate the derivative by differentiating each term separately. Okay, we are doing similar thing here. If this converges on some interval I, then the derivative and the integral converges on I. As noted below, behavior at the endpoints of the interval must be investigated individually. Evaluating the derivative and indefinite integral in this way is called term-by-term differentiation of a power series and term-by-term integration of a power series respectively. The ability to differentiate and integrate power series term by term also allows us to use non-power series representations to find power series representations for other functions. Okay, for example, given the power series for f of x 1 over 1 minus x, we can differentiate term by term to find the power series for 1 over 1 minus x squared. Wait, hold on. Just realized one thing. If 1 plus x equal to 1 minus x, minus x plus x square. Uh, so this is a geometric series which converges if minus x is less than 1 or x is less than 1. Using the formula for the geometric series, convergence of geometric series, we are left with this. So if we integrate both sides, infinity uh, hmm, if we integrate this, so integral of this is integral of this is x, and then we have minus x square, oops, Shouldn't there be plus c over here? If I write 1, but the thing is, we need to check if it converges, right? But I think we already did that. So let's assume this converges, then we have the alternating harmonic series. Which is equal to ln of 2. But shouldn't it be ln of 2 plus c? I guess it would make more sense if I did this. So the 0 part wouldn't matter. So now I don't have to worry about the plus c. The thing is, this is assuming that it converges at 1. Suppose that the power series Cn x minus a to the power of n converges on the interval a minus r to a plus r for some r more than 0. Let f be the function defined by the series. Okay. For some interval, then f is differentiable on the interval a minus r to a plus r. And we can find the derivative of f by differentiating the series term by term. Also, to find the integral of f, we can integrate the series term by term. The resulting series converges on a minus r to a plus r. We have this. So derivative of this is this. So we derivate each one, we get a 1 plus 1. No, so sorry, 0 plus 1 plus 2x plus 3x cubed plus, no, 3x squared plus 4x cubed. Right? Let me see what they do. Yeah, we got this. If this converges on interval I, then so does, if this converges interval I, so does its derivative, right? Plus 1 isn't going to work, but minus 1 can work. Okay, so this is equal to this. If we are trying to calculate this, we substitute x as 1 over 4. Then we get 16 over 9. Also, one thing that's bothering me, if this is equal to 1 over 1 plus x, let me think. Suppose, okay, I have a geometric series minus 1 and then multiplied with x, multiplied with x, multiplied with x. This is infinity minus x to the power of n. 1 minus r is equal to minus 1, 1, and then it's minus x, so plus x. This is if this is less than 1, so derivative is 1 over derivative. Okay, so if I take the integral, I get I can bring the minus outside over here, and then I get I can do this x plus x squared over 2. Wait, I'm just checking something. Now, I was trying to do this for the harmonic series and seeing where it leads me, but it doesn't work. Integrating the power series. We already did this, right? ln of 1 plus x, assuming that x is less than 1. It's -1, we get a harmonic series which diverges. So that endpoint doesn't work. If it's +1, how do we show that it converges? I have no clue. We already showed that, but I don't really understand the proof. And we can just plug in 0 to find C. Uniqueness of power series. Okay, great. Overview of the Taylor series. Consider a function f that has a power series representation at x is equal to a. Then the series has the form like this. What should the coefficients be? For now, we ignore the issues of convergence, but instead focus on what the series should be if one exists. We return to discuss convergence later in this section. Equating the series at x is equal to a, we see that it is C0. Thus, the series equals f of a if the coefficient C0 is equal to f of a. Okay, wait, let me understand what they're doing. So you have this. And then f of a is equal to, all of them will cancel out and then C0 will remain. Then what's next? The derivative is C0 will remove. The derivative is C1 plus 2C2 plus 3C3. Oh, I see. If the derivative at A is C1. I think I got an idea of what they're trying to do. Derivative is C1. Most probably the second derivative is C2. So basically, N is C N. Maybe that's what they're trying to say. Oh no, they were doing something else. Then so any series it's f of a and then divided by 2. That would be C1. Hold on. We have C0. Then when we take all the derivative, we are left with C1. We took the derivative again. Left with 2C2. I think it's 0 factorial, 1 factorial, 2 factorial, 3 factorial. Yeah. It's n factorial. Cm. This is known as the Taylor series, and if it's 0, Taylor series for f at 0, it's known as the Maclaurin series. Do they mean centered at 0? Or do they mean when x is 0? To determine if a Taylor series converges, you need to look at its sequence of partial sums. These partial sums are finite polynomials known as Taylor polynomials. But how do you know it converges only up to a point? And that point is very far away. Like if that point is very far away, I don't think this is a good method. Maybe it's an alright method. If a is equal to 0, then these polynomials are known as Maclaurin polynomials. So these are the nth partial sum of the Taylor series. If f has n derivatives at x is equal to a, the nth Taylor polynomial for f at a is this. Finding the Taylor polynomials. Okay, let's try this. F of x, ln of x at x is equal to 1. Hold on a minute. Can any function be represented as a power series? Like, do we assume it has a power series representation? Okay, well, let's assume it does. And of x, we are left with so that's like we are finding at x is equal to 1, right? Ln of 1 plus derivative of 1 over x is derivative of ln of x is 1 over x. So 1 x minus 1 derivative of 1 over x is minus 1 over x square, which is also 1. But we are doing half, right? So half x minus 1 squared. Ln of 1 is 0. So we can just forget about this. Plus it with 1 over 3 factorial. Is this good enough? I mean, I found some of them, but ln of x 1 over minus 1, 2. Wait, why 2? No, hold on. 6 goes above, right? But the thing is, would it be equal to ln of x? And what if it doesn't converge at that point? So for e to the power of x, we have, let me get rid of this. We, at what point? It's just e to the power of x. Oh, Maclaurin polynomial, so 0, right? So 1 plus derivative of e to the power of x is e to the power of x. At 0 it would be 1, so we are left with x. And then half x squared I think it's easier if I write factorial. But this is at 0. I know I derived like this is equal to e to the power of x separately, so I know the convergence is infinite. As for sine x, we have sine a, sine 0 is 1. No, wait, sine 0 is 0. Okay, derivative of sine is cos. Cos 0, hold on, sine 0 plus, just write S and C. Derivative of cos is minus sine over 2 factorial. Derivative of sine is cos. This is equal to sine x. But the thing is, how do we know this works for all functions? Or are we just assuming? Sine 0 is 0, cos 0 is 1. X sine 0 is 0, cos 0 is 1. Wait, hold on. Derivative of sine is cos. And then I'm guessing the next one would be 0, because there would be some minus sine 0. Derivative of cos is minus sine. Derivative of sine is cos. So I'm guessing the next one would be the power of 7. Wait, what's happening here? They have the wrong image here. Taylor's theorem with remainder. Recall the nth polynomial for a function f at a is the nth partial sum of the Taylor series for f at a. Therefore, to determine if the Taylor series converges, we need to determine whether the sequence of Taylor polynomial converges. However, not only do we want to know if the sequence of Taylor polynomial converges, we want to know if it converges to f. To answer this question, we define the remainder Rn of x is equal as Rn f of x minus Pnx. Okay, what are they doing here? For the sequence of Taylor polynomials to converge to f, we need the remainder Rn to converge to 0. To determine if Rn converges to 0, we introduce Taylor's theorem with remainder. Not only is this theorem useful in proving a Taylor series converges to its related function, but it will also allow us to quantify how well the nth Taylor polynomial approximates the function. Here we look for a bound on Rn. Consider the simplest case, n is equal to 0. Let P0 be the zeroth Taylor polynomial at A for a function f. The remainder R0 satisfies. Okay. If f is differentiable on an interval I containing a and x, then by the mean value theorem, there exists a real number c between a and x such that f of x minus f of a is equal to derivative of c times x minus a. Hold on, what are they doing here? Hold on a minute. Okay, let me think about this. If f is differentiable on an interval I containing a and x, then by the mean value theorem, there exists a real number c between a and x such that f of x minus f of a is equal to derivative at c. There's a point c. It's the derivative c is equal to x minus a. I want to see how it's done with Pn. Okay, for some real number c between a and x, it is important to note that the value of c in the numerator above is not the center a, but rather an unknown value c between a and x. This formula allows us to get a bound on the remainder Rn. If we know what will happen to f of n plus 1 x. Okay. Okay, let me understand what they're doing. There exists a real, then for each x in the interval I, there exists a real number c for between a and x such that this formula, if there exists a real number m such that f, the n plus 1 derivative of f is less than or equal to m for all x below, for all x and I. Okay, I'm getting confused by this. Consider a function f of x is equal to the third cube root x. Find the first and second Taylor polynomials for f at x is equal to 8. So this would be we are doing, so a is equal to 8, right? A is equal to 8. They said first and second Taylor polynomial. Is first p0 or p1? No, first is p1. So this f of a plus it with derivative of f now let me write 8 to the power of 1 over 3 um like that maybe, but where is the x? This is the derivative. Let me think about this. No, not this. This times it by 1 over 3 and then minus 1. And okay, if we second derivative over 2 minus 2 over 3, 2 over 3, then minus 3 over 3, 8 squared. So what about this? Hold on, what's the value of this? I wanted a fractional value. Yeah, it seems like I did it correctly so far. 2 plus 1 over 12. This is 2, that's correct. This is 1 over 12. Okay, and this is 1 over 288. Okay, that's correct. But the graph I got is different. Plus, minus. No, I'm timesing it. Hold on, this is plus. This is minus. Use Taylor's theorem to bound the error. Error is 0.006514. But I'm still confused by this. The Maclaurin polynomials for sin x are given by this. Find the fifth Maclaurin polynomial for sin x to approximate sin pi over 18. Bound the error. I mean, they gave it to us, but representing functions with Taylor and Maclaurin series. Find the Taylor series for f of x is equal to 1 over x at x is equal to 1. Determine the interval of convergence. So the Taylor series of 1 over x is equal to 1 over a plus derivative just minus 1 over a squared, and then we do x minus a, and then we do minus 1 again. If a is equal to 1, then minus x minus 1 plus x minus 1 squared so it's like plus minus and so on. How do you determine the interval of convergence? Determine the interval of convergence. We use the ratio test. We find that, get this. Thus, the series converges if x minus 1 is less than 1. That is from 0 to x to 2. Suppose that f has derivatives of all orders in the interval I containing a, then the Taylor series converges to f for all x and I if and only if the remainder is 0. To prove that the remainder goes to 0, we typically use the bound. This is to prove from Taylor theorem with remainder. I'm not satisfied with the remainder part. Still quite confused. So I think when they're presenting this, I think it would be better with R2 or R1. Hold on, let me see if I can understand this. Fix a point x in I, introduce the function g such that, hold on. Okay, gt is f of x minus f of t, or they're subtracting the Taylor series. The remainder is basically the rest of it. Shouldn't gt be equal to 0? We claim g satisfies the criteria of Rolle's theorem. Since g is a polynomial function in T, it is differentiable. It is a differentiable function. Also, g is 0 at t is equal to a and t is equal to x. And let me understand what they're doing. So this, the f of x, and then they're subtracting the Taylor polynomial minus r and x. So this is the Taylor polynomial, but where a is equal to t, using the product rule, we have this. Consequently, derivative of g is minus f of t plus, a lot of it cancels out. Notice that there is a telescoping effect, therefore we are left with this. By Rolle's theorem, we conclude that there exists a number c between a and x such that gc is equal to 0. Derivative of g at c is equal to 0. We conclude this. And then, okay, I can see how they got this. From this fact, it follows that if there exists m such that derivative of the n plus 1 derivative of f of x is less than or equal to m for all x and I, then the remainder is also less than all of this. if the remainder goes to 0, then for e of x and sine x is 0. If this, but they're using the ratio test here. Okay, they use the ratio test and then they said the series converges absolutely for all x, and thus the interval of convergence is minus infinity to infinity. To show the series converges to e of x for all x, or they only use the ratio test for the nth Maclaurin polynomial. Now, to show that the series converges to e of x for all x, we use the fact that the nth derivative of x is equal to e of x for all n greater than 0. And e of x is an increasing function on minus infinity to infinity. Therefore, any real number p, the maximum value of e of x for all x less than or equal to p is e to the power of p. Thus, we have shown this. Since we just showed that this converges for all x by the divergence test, we know that this is equal to 0. When did they show this? Oh, I think over here. Using the nth Maclaurin polynomial for sine x, we find the Maclaurin series for sine x is given by this. Which goes to 0 for all x. We obtain the interval of convergence as minus infinity to infinity. To show that the Maclaurin series converges to sine x, look at Rnx. For each x, there exists a real number c between 0 and x such that this is true. Okay. I need, like off stream, I need to take some time understanding this. Is this the last one? Okay, let's see. In the preceding section, we defined Taylor series and showed how to find the Taylor series for several common functions by explicitly calculating the coefficients of Taylor polynomials. In this section, we show how to use those Taylor series to derive Taylor series for other functions. We then present two common applications for power series. First, we show how power series can be used to solve differential equations. Second, we show how power series can be used to evaluate integrals when the antiderivative of the integrand cannot be expressed in terms of elementary functions. E to the power of minus x squared, an integral that arises frequently in probability theory. So, binomial series. Our first goal in this section is to determine the Maclaurin series for the function f of x is equal to 1 plus x to the power of r for all real number r. The Maclaurin series for this function is known as the binomial series. We begin by considering the simple case r is a non-negative integer. So what are they trying to show? 1 plus x, 1 plus 2x plus x squared. Okay, this is the binomial series. The expression on the right hand sides are known as a binomial expansion. Right, we are expanding them like this. So we have a function 1 plus x r to the power of r. Maclaurin series would be shown like this. So far I understand. We donate if r is a non-negative integer, then r plus 1 first derivative if the r plus 1 derivative is a zero function, is the zero function, and the series terminates. In addition, if r is a non-negative integer, then the equation 6.8 for the coefficient agrees with equation 6.6. Oh, like I get what they're doing. This and this is matching. More generally, to denote the binomial coefficient for any real number r, we define this. In this notation, we can write the binomial series for 1 plus x to the power of r as this. Wait, we can use the Maclaurin series to prove that the binomial theorem works even for negative integers, like negative exponents. If we apply the ratio test, we see this. If x is less than 1, then the series would converge. Sorry, I'm just checking something. The Maclaurin series for 1 plus x to the power of r is a binomial series. What if r is negative? It wouldn't be a binomial series, right? Okay, so we are expanding this using the binomial series and just plugging x as 0.5. Guess what they're doing? The remainder part still confuses me, but I will read about that later. You just do, instead of cos x, we just put root x, right? When in the interval of convergence, we minus infinity where root x is between minus infinity to infinity. Of course, here we use e to the power of x. We see that the nth term in the Maclaurin series for sin h is given by this. For n even, this term is 0. For n odd, this term is 2xn over n squared. Therefore, the Maclaurin series is this. Wait, how did they get this? Did they do it manually? Use the binomial series to find the binomial series for this. Isn't it just minus half? Derivative of this is this. Derivative of this, which is equal to, wait, I don't understand. Oh, so you use binomial series to open this. Where is it? And then you differentiated each term. Okay, I guess I understand. Solving differential equations with power series. Okay, I will just read that one and then I will end the stream because I need to read it upstream to actually understand. Consider the differential equation derivative of y is equal to y. Recall that this is a first order separable equation. Its solution is y is equal to c times e to the power of x. This equation is easily solved by using techniques discussed earlier in the text. For most differential equations, however, we do not yet have analytical tools to solve them. Power series are an extremely useful tool for solving many types of differential equations. In this technique, we look for a solution of the form y is equal to c n x to the power of n. Determine what the coefficients would need to be. In the next example, we consider an initial value problem. Derivative of y is equal to y to illustrate the technique. Use power series to solve the initial value problem. Suppose that there exists a power series solution. Differentiating this series term by term would give us this. If y satisfies the differential equation, then this is equal to this. Oh yeah, because the derivative of y is equal to y. C0 is equal to C1, C1 is equal to 2, C2, C2 is equal to 3, C3. Using the initial condition, y0 is equal to 3 combined with the power series representation, we find that C0 is 3. Okay, that makes sense. C0 is 3, which is also C1. So then C2 is 3 over 2. Then C3 is 3 over 3 factorial. Then C4 is 3 over 4 factorial. But this is only assuming if it has a power series, right? Yeah, this actually makes sense to me. I thought it would be difficult. Power series. So y0 is a derivative of y0 is p. So let's say yx is equal to and then I have this. and then derivative of this would be c1 plus it with two c2 plus it with 3. And then the double derivative would be, this would be 0. So we are left with 2 c2 plus it with 3 times 2 plus it with 4 times 3. Yeah, this is from the first derivative. This is from the second derivative. If they're equal, wait, if they're equal, then I got this. So I have c2 is equal to 0. Hold on. No, wait, actually. Let's start with this. C0 is equal to 3 times 2 C3. C1 is equal to 4 times 3 C4. And then Cn, sorry, no wait, n minus 1 Cn minus 3. This is the general formula. However, C2 is equal to 0. C2 is equal to 0. But C2 is also equal to 5 times 4 C5. C3 is equal to six, 5, C6, C4 is equal to 7, 6, C7. And then C5, this will be my last one. 8, 7, C8. However, C2 is 0, then C5 is 0. C5 is 0, then C8 is 0. C2 is 0, then C5 is 0. But if C5 is 0, then C8 is 0. But if C8 is 0, then I think it's plus 3. C11 is 0. So some of them are skipped, right? Y0 is A, derivative of Y0 is B. Y0 is equal to A derivative of Y0 is equal to C1 which is B. This is C1. Now let me think about this. A so this and this would be equal. Wait, what did they do before? Oh yeah, we are finding y. Y is equal to A plus B. Wait, hold on. A plus bx plus x squared does not exist. C2 is 0 and then C3 is 3 times 2 and then C4 is C1 which is B 4 times 3. Hold on. A 3 times 2 x cubed plus b 4 times 3 x to the power of 4. A x 5 is skipped. 6, which I would do 6 times 5. 8, hold on. Is it 6 times 5? It's C3, right? 3 times 2 times 6 times 5. Three. I'll just write it on text. 3 times 2 times 6 times 5. This pattern is difficult. This is what I found. Yeah, this is what they found also. 6 times 5 times 3 times 2. So, but how do we? Okay, never mind. We remark that the term elementary function is not synonymous with non-complicated function. For example, the function is an elementary function. By elementary function, we mean that a function can be written as a finite number of algebraic combination or composition of exponential, logarithmic, trigonometric, or power functions. Isn't this an elementary function? Or the antiderivative of the integrand is not an elementary function. Because you need finite number of algebraic combinations. Right, express this as an infinite series. Let me think. Then we need to express e to the power of minus x square. Let me think about this. So the power series would be this is when it's centered around 0. This is x square. Right, and then x cubed and so on. So f of 0 is 1 plus it with the derivative of the outside times it by the derivative of minus x squared, which is minus 2x. And then the double derivative would be the derivative of this. So the derivative of this is e to the power of x minus 2x. Hold on. Shouldn't it be derivative of first times the second times it by minus 2x plus the first times the derivative of the second? Which is equal to wait, you need to express as an infinite series. So this divided by 2 factorial times it by x square. I don't know if I'm doing this right. Two x minus 1. Because there's a 2 here. Then I can... Let me think. There doesn't seem to be a pattern. So derivative of this, derivative of the first, times the second, plus the first times the derivative of the second. Let me see if there's a common pattern. Minus 4x squared I don't know if I did a mistake anyway. I did do a mistake. This is 4x squared. This is 4x squared. Then, okay, I took 2 out. Derivative of the first, which is all this. Times the second. It's the first times the derivative of the second, which is 4x. Let's see. Minus 4x cubed minus 2x plus 2x plus 4x, which is 6x. Maybe there is a pattern to it. Let me think. This is minus 2x. This is 4x squared minus 2. This is minus 8x cubed. Or maybe there's no part into it. Plus 12 minus 8x cubed plus 12. Wait, hold on. How did they get this? This was the difficult part, right? I know why. E to the power of x minus x squared. Wait, if the derivative at 0 is 1. But the double derivative may not be 1, right? No, wait. The derivative is 0. Oh, I know. The derivative is 0. No, wait. Derivative of the derivative. How are they getting this though? Oh, e to the power of x. Taylor series for e to the power of x, and then they plugged in minus x squared. I see. And then they integrated both sides. Then they got something like this. As mentioned above, the integral arises often in probability theory. Specifically, it is used and studying data sets that are normally distributed, meaning that the data values lie under a bell-shaped curve. For example, if a set of data values is normally distributed with mean mu and standard deviation sigma, the probability that a random chosen value lies between a and b is given by this. To simplify this integral, we typically let c equal x minus mu over sigma. Okay. Okay, I guess I will. Would it require Taylor series and sequences and series for the next chapter? Because I want to finish calculus 2 and get back to Taylor series to fix my understanding. Parametric equation and polar coordinates. Okay, I think I will end the stream here. And then next stream I can start working on parametric equations. Okay, then. I guess see you next time.